Okay, so last speaker of this morning, Sujatha Ramdorai, University of British Columbia, and she's talking about Iwasawa invariant for elliptic curves in a family.
Thank you, and I would like to thank the organizers for the invitation and the opportunity to speak here. It's nice to see familiar faces, old friends, students. I'll try to keep looking at the watch, but in case I forget and I'm going past the time, just stop me here. So P is a rational number and most often odd, though some parts of it works even for 2, but I'll play chicken and I'll assume P greater than or equal to 3. It's rational prime. And E over Q, as usual, elliptic curve with good ordinary reduction. K over Q will be a totally imaginary quadratic extension. But in fact, again, this can be totally imaginary. Though initially we started with the case where we were working in a CM elliptic curve context. So totally imaginary quadratic, E with CM, etc., etc. But then we realized that some of our results are more general. So I'll assume that it's totally imaginary, but abelian extension. And again, this is a vestige from our original case. Yeah, I forgot to say all this is joined with work in progress. Parts of it are done, but we are still hoping to extend. Okay. Okay, so let me write it here. All this is joined with Søren Kleine from Munich and Ahmed Matar from UAE. I forget which university he is in exactly, but so K infinity is a ZP2 extension. So again, this is because we started with a CM context, but then realized that it can be, the scope is broader. So this is a ZP2 extension containing K cyclotomic, the cyclotomic ZP extension. So I'll use this notation throughout. For any field, when I write F cyclotomic, it means that I'm considering the cyclotomic ZP extension of that field. And I won't mention the P because I'm sort of fixing it. And this is the cyclotomic ZP extension of K. And I'll choose a finite set of primes S, which contains SP. This will again be standard notation. This will be the primes above P of the corresponding field extension that I'm working with. And the bad primes for the elliptic curve, that will be denoted as bad. This will be a finite set of primes, which contains these primes of K. But usually I might have to work with a corresponding set for extensions of K. So it should be clear when I write SP as bad that that's what is meant. And as usual, Ks over K will be the maximal unramified outside S extension of K. We'll have G. This will be the Galois group of K infinity over K. So we'll keep, so I have Q, I have K, K cyclotomic, K infinity, and all this is happening inside Ks. This will be my G. This is a 2-dimensional periodic Lie group. And I'll identify the corresponding Iwasawa algebra. I'll write it as lambda 2 because I'll later specialize to in between ZP extensions of G. So I'll write a lambda 1 so that it means that I'm working in a 1-dimensional compact periodic Lie group, and this is lambda 2. So then, of course, this is isomorphic to ZP. TU, I'll choose a pair of topological generators. So G is going to be topologically generated by, say, tau sigma, and then tau will correspond to 1 plus T, and then sigma will correspond to 1 plus S. So these are the identifications. I don't think I'll need them, but when we are writing about the details, which I'm not going to do in the proofs here. Sorry, you. Thanks. Yeah. So when we really have to do the proofs, then we need these identifications and so on when we specialize, but I'm not going to be talking so much about proofs. Okay. So long ago, Greenberg, in one of his early papers, just after Iwasawa's work, the idea was, of course, Iwasawa in the cyclotomic ZP extension, you had the lambda invariant, the mu invariant, and then the famous Iwasawa's formula on the growth of class groups. Right? Then there was this question about what happens when you want to do this study over other ZP extensions. You can still define that the definition of mu and lambda is really coming from algebra. There's not really any number theory. You can define it using structure theory that works for modules over this power series ring in one variable over ZP. And that's where these invariants are coming from, the lambda and the mu invariant. So you can ask this question of how lambda and mu invariants vary when you vary the ZP extension. Instead of a cyclotomic extension, you take other ZP extensions, then what happens to the lambda and mu invariant? And this was kind of formalized by Greenberg in one of his very early papers. I think it was in American Journal of Math, I'm not very sure, where he asked this question over, he calls it arbitrary gamma extensions of a number field or something like that. And then there he actually makes a family. So this is, let's say this is the set of all ZP extensions of the number field. Okay, and then you can actually think of E naively, but also in a very precise sense as P1 over ZP. And we'll, for our purposes today, we will just think of P1 of ZP as pairs, just as lines in ZP. So think of it as A comma B, where A and B are in ZP, both not divisible by P. And you identify AB with A prime, B prime if they differ by a constant T, which is a unit in ZP star. Okay, so whatever you do with the usual P1 of fields, there's an easy analog. Think of P1 of R, for instance. So you're doing something like that for P1 of ZP. And so if I take a pair, I think of anything here as a pair AB, where AB are really in ZP, both not divisible simultaneously by P. And then there's an identification, AB equals A prime, B prime. If A is T times A prime, B is T times B prime, and T is a unit in ZP. So when you do that, then the corresponding ZP extension, I'm going to take the topological closure of this subgroup. This makes sense. Sigma to the power A, tau to the power B, and that gives you a ZP extension. And well, I want to take the fixed field of this. So the process is this. So take the corresponding topological subgroup, and I will call this HAB, though I'll drop this HAB and then just write H or H prime. That will usually denote some intermediary extension, K prime, where this is an H or an H prime, and this is isomorphic to ZP. Okay. So HAB is the subgroup of G, and this is generated by topological closure of this subgroup, topologically generated by, okay. So these are all the ZP extensions. And then the question was, what happens to these invariants when you study this class of ZP extensions inside ZP of 2? And Greenberg had some conjectures in this regard. And later on, Greenberg, in fact, even introduced a topology so that this bijection actually becomes homeomorphism, topology on E. So you say, take an element which is an intermediary ZP extension here, and then you define a neighborhood. This will form the base, a topological base for all the neighborhoods. You want to define what a small open set around this element L looks like. So this is going to be, I'm just writing it in words, all ZP extensions such that up to the nth layer somehow they are the same. So which coincide with L, with the extension that you have, at least up to n, up to this integer n. So n is a natural number. So this gives a topology on the set of all ZP extensions around L, and this forms a base of the neighborhoods. This is what Greenberg considered. And so with this actually becomes a homeomorphism. Then get a homeomorphism. From E to P1 of ZP. And I'm still in this, I'm going to now talk about the Selberg group. Of course, initially a lot of this work was done to the study to understand the class groups, how they behave in all these ZP extensions. And what we are interested is in trying to understand the corresponding picture for Selberg groups. Okay, so this will be my notation. So when I work with any such K prime, so in general, for any extension L, anywhere, infinite, finite, whatever. So let me write X of E over L. This is the Pontryagin dual of the usual Selberg group, the P infinity Selberg group of E over L. So of course, this is discrete. So we take the compact object, and of course, this comes with a Galois action viewed as a Galois module. So if it is a finite extension, then it will just be over the group ring. And if it's an infinite extension, we will view it as a module over the Iwasawa algebra. So I will just write Galois module, respectively Iwasawa module.
May I ask a question?
Sure.
Script E, does it really parameterize all ZP extensions of K or just the ones contained in a particular
Oh, yeah,
K
I'm sorry.
infinity?
So all of these are inside K infinity.
Mm-hmm.
Okay, so yeah, X contained inside K infinity.
I suppose if K is imaginary quadratic, there really is only a two-dimensional
Right.
family.
But for today's talk, I'll mainly be interested in K infinity. In fact, you can do something like this. Instead of a ZP2 extension, you can take a ZPD extension.
Yeah.
And then in general, ask what is happening for the ZP extensions inside that ZPD extension.
Mm-hmm.
But for today's purposes, we'll do that. And Greenberg originally, he did this in a wider context where he took ZPD and so on.
I see. Thank you.
Right. Okay. And so then I'll also use the following. So if H prime, so now I'm taking a ZP extension. H prime is contained in G and H prime is isomorphic to ZP. Then of course we can take the fixed field under this and then that will give me an element in E. H prime is here. So this is of course contained in K infinity. So then we can ask such questions over these fields. And I'll usually go to the corresponding field by looking at something here and then taking the fixed field. Okay, now this is somehow too large for even the questions that we are asking. If you look at the original paper of Greenberg, he had a lot of conjectures about the behavior of mu, how bounded it is, or lambda, whether it can be absolutely bounded by an absolute constant, things of that kind. Now, that's already too large for us to say something like this over all the ZP extensions. So we will narrow down to this following, because that's where we can say something quite sharp. And in fact, this is not going to be a talk, even though I'm starting from below, in the sense I'm looking at K and looking at ZP extensions above K, inside K infinity, we will approach it from the top. In the sense I'm going to look at ZP quotients of K infinity over K. Okay. So definition, so I'm going to take this subset. So again, this will consisting of all subgroups in this parameterization, these topologically generated by these. Because now, because of that homeomorphism, I'm thinking of everything in terms of this parameterization, such that H is topologically generated by this pair sigma A tau B for AB in this P1. Then second, because again, these hypotheses are necessary because whatever early results that Greenberg proved were under these hypotheses. You want to understand the phenomena of what's happening over cyclotomic ZP extensions for other ZP extensions, but they need some properties. So no prime in S splits completely in this fixed field. And then the third property, the property that we know about the behavior of P. So every prime in SP is totally ramified, or ramifies is enough. Ramifies in K infinity H over the cyclotomic extension, of course, it's totally ramified. And then the final property, this is Mazur's conjecture, right, for the cyclotomic extension, and we want to transfer that to these other ZP extensions, namely that the dual, the Pontryagin dual of the usual P infinity Selma group is lambda 1 torsion, or I'll write this as lambda G mod H module torsion. So when you work with H, which is the extension of the cyclotomic up to K infinity, then this is a usual conjecture which we know for a large number of cases, for instance, for CM elliptic curves and so on. You know that it's a torsion lambda G module. And we want to make that hypothesis. Okay, so now let me come to the questions. What is our work motivated by? So that is, I already alluded to some work of Greenberg. So that's part of the motivating question. We want to imitate what was done initially for class groups. We want to understand what can we say, the corresponding results, what can be said for the Selma groups. That's one motivating question. But now here is where this part about coming from the top becomes relevant. In a paper, I forget when, but John Coates was absolutely convinced that there is a higher dimensional analog of Mazur's conjecture, which says that this is torsion, right? So Mazur's conjecture is, of course, for ZP extensions. So by the structure theorem, we know that if you take a finitely generated module, up to ignoring finite groups, you have a part which is coming from the mu invariant, and then another part coming from the characteristic polynomial. So if you forget the mu invariant part, what you get is a finitely generated ZP module. So if you think of ZP gamma, the usual cyclotomic extension, then the H, that is what stands above the cyclotomic extension, is nothing, it's the identity. So once you kill the P part, then it becomes a finitely generated ZP module. And John Coates's belief, strong belief, which he very strongly held, was that if you more generally consider a wider class, not just commutative extensions like this, but even those coming from the non-commutative extensions. For instance, take the trivializing extension for the Galois representation coming from the elliptic curve, or take the false state extension, the Kummer extension on top of the cyclotomic extension, and so on. So then you have this part, which is an H. And in fact, in our original paper, this part was called H, the Galois group from K infinity down to cyclotomic. So typically it's an SL2 ZP if you're working in a non-commutative setting. Or in the CM setting, this is just going to be another gamma, another ZP extension. And we call this the MH of G conjecture. Let me put a cyclotomic because I'm going to now vary H over all ZP extensions. So H cyclotomic will be the Galois group in our setting as here. K infinity over K cyclotomic. But like I said, the conjecture was made more generally, even for a wider class like the non-commutative extensions and what we generally call the admissible periodically extensions. So then there you have X of E over K infinity, the usual dual Selma group, which is now a finitely generated, and you know examples where it is in fact torsion. So it's in general conjecture to be torsion, and you have examples where this is torsion, even in the non-commutative case. So this is finitely generated torsion lambda G module. And let's look at this module, Y of E over K infinity, which everything is Noetherian inside. We are in the best case But even in the non-commutative world, we are in a good case because everything is Noetherian. So you can talk about the p primary torsion part, which is actually a submodule. So this will denote the p primary part. So you kill that. And then the MH of G conjecture says that this should be a finitely generated lambda H module. So the only thing that prevents, the only thing that contributes to not working over this part is the P part, which is exactly like killing the mu invariant. If you kill the mu invariant, you get a finitely generated ZP module. You just get the lambda invariant. And the belief was that this lambda H rank, so once if you have this conjecture, this MH of G conjecture, then because this is a finitely generated lambda H module, you can talk of the lambda H rank of this module. And again, the belief was that, and there is evidence to do this as well. Some of my students who are here, they have done that in their thesis, and others have taken it forward, is that once this holds, then you can talk of the lambda H rank of x of e over k infinity, right? Or rather, let's kill the mu invariant part so we can even, in fact, you can talk of the lambda H rank of x of e over k infinity, by which you just mean the lambda H rank of this y of e over k infinity, because what you're killing is the p primary torsion. Typically, this will be a pseudo-null submodule, and in most good cases, you know that it has no non-zero pseudo-null submodule. So this will be, you can define the lambda H rank, which for today's purposes, let's assume is the lambda H rank of this, which exists if you believe the MH of G conjecture. And the belief was that this should play the role of the lambda invariant. So I'll say this in inverted commas, should play the role of the usual lambda invariant for ZP extension. Okay, so what do I mean by this? What does one mean by this? So for instance, if you look at classical Iwasawa theory where you're working over ZP extensions, you know a lot of results about lambda invariance. What is, for instance, the famous Riemann-Hurwitz formula? How does the lambda invariant change when you go up a finite extension? Right? Or if you have isogenous elliptic curves, then how does the lambda invariant compare? How does the mu invariant compare, as well as you say you study the lambda invariants in a family and so on. So the idea was when you treat this part from k infinity to k cyclotomic, and then you study the lambda H rank, then whatever the classical results you had for the lambda invariants, there should exist a version of that for this part when you study it as modules over this Iwasawa algebra. And again, there's evidence for that. And this comes in quite useful, for instance, when you want to study other modules, Iwasawa modules over families and so on. So the motivating question for us now again is we want to understand what can we say about this MH of G conjecture when I know something, let's say I know it for the cyclotomic extension. Then what can I say for other ZP extensions? So now I'm back to this situation. So I have my K cyclotomic extension. And now by Greenberg, I can look at a neighborhood of this extension, say. Then I have other ZP extensions. Then if I know the MH of G conjecture for, let's say, for the cyclotomic extension or for any other object in between, what can I say about it in a family? And this results like this have been done for the lambda invariant. The classical lambda invariant, there are conjectures and results as well. If you know something about the lambda invariant for the cyclotomic extension, what can you say for the lambda invariants for other ZP extensions in a neighborhood of the cyclotomic extension? So this is what I meant when I said we are going to come from the top. So suppose we know MH of G conjecture, let's say for the cyclotomic extension, then what can I say about MH of G conjecture for other H in the neighborhood of the cyclotomic extension? Okay, so that was one of the motivating questions. And again, we were guided by what is known for lambda invariants. And what is known classically for lambda invariants comes from various papers of Guoco, Monsky, and also Greenberg. Guoco, Monsky, and all of them together, they have written a fair number of papers. And I would be very happy if somebody in the audience is familiar with those papers and could explain them to me, because it seems that many people use it. Søren is one person who's worked a little on it, but I tried talking to many others. In fact, I even got in touch with Monsky, who says, excuse me, but all this was done a long time back. And I've tried asking commutative algebraists who seem to use a part of Monsky's result in commutative algebra very strongly. And those results in commutative algebra were originally inspired by questions coming from number theory. You know, the Hilbert-Kunz function, the Hilbert-Kunz multiplicities, and so on. So the commutative algebraists seem to be using Monsky in full force and so on. But again, many of them say, oh, we only know the commutative algebra part. We don't know the arithmetic part. And if you look at Monsky's papers, there are many of them, and he changes the words, he changes the notation, so you don't know what was meant where and so on. Anyway, so in these works, in these series of works, what they do is, so they work with more generally not ZP2 extensions, but ZPD extensions. Okay, and then for any such ZPD extension, when you take the class group over the ZPD extension, or even when you take the Selma group over such a ZPD extension, for any module over such ZPD extension, they define what's called, there are two invariants. There's an M0 invariant, which is supposed to be a vast generalization of the mu invariant. And in fact, when D is equal to 1, it coincides with the mu invariant. So this is the analog of the mu invariant. Okay. And then they have another invariant, which is called the L0 invariant, which in the case of D equals 1, this coincides with the usual lambda invariant. And then in their work, they do exactly this. They study what happens to L0 when you take two extensions contained inside a ZPD extension, whose quotients are ZT, right? So in our case, it will be like taking two extensions, H and H prime, whose quotients are ZP extensions. So they study the behavior of this. And so our questions and results were motivated by what is known in this case. So Greenberg, let's start with, I would like to quote this result of Greenberg. He proved this result, and in fact, he also made a conjecture as well. So he conjectured that something like this should hold in general for ZPD. So, but here is the result that he proved. So you take K over K. K is a number field. Now let me change notation a little. So K is any number field, not necessarily quadratic imaginary or anything. K is any number field. And then you have K over K, a ZP extension. And such that you have the same hypothesis as in that script H. So primes of SP, but this time you don't want totally split. It's enough if they are, I mean, they're, okay. This was Greenberg's original statement, finitely split. And then he needs this assumption. If the mu invariant of K over K is 0, this is the usual mu invariant, no elliptic curve, nothing in this case. This is the usual mu invariant for a ZP extension, the Iwasawa mu invariant. So if this mu invariant is 0, then there exists a natural number n such that this mu continues to be 0 in a neighborhood of this ZP extension under the topology. Mu K tilde over K is equal to 0, and lambda in this neighborhood K tilde K for all these K tildes in the neighborhood of K, it's bounded by a constant. This is for all K tilde, which belongs to a neighborhood of this K under this topology in a base, and some fixed constant. So in a neighborhood, the lambda invariant is bounded. Sorry? Okay, that again, there's a series of papers. So initially, I think they proved that it can be attained. And then Kutzko and Monsky, at least Monsky in so many of his papers, when he tries to generalize this for ZPD extensions, there is this question. Does this work even for M0 and L0? And then ultimately he proves that M0 can be as big as possible. And lambda, he says, I still don't know. So in some papers, he says, I believe it has to attain this bound and there has to be a bound. In some other papers, he says, I don't see why there should be a bound like this and so on. So nobody knows. At least I couldn't dig out a fact from that, but it's very interesting, those papers. Okay. And then later, Kleine improved on this result of Greenberg. So he proves, so again, K over K, but now this time K is not the cyclotomic ZP extension. And then again, you have this hypothesis that each prime in the primes above P is finitely split, which lies above. So I mean a K in K, which is lying above an SP of K. This is finitely split in the ZP2 extension. Taken by this composite K dot K cyclotomic over K. This is now a ZP2 extension. And you make this hypothesis, then you have a similar result. Then there exists N in N such that this mu invariant K tilde over K is less than. Now you see, you got rid of this hypothesis that it is 0. So in a neighborhood, it is bounded by the mu invariant of your original K. Okay. For K tilde in this neighborhood, some, what did I call it? Kn. Like this. And then you can give an explicit, and this here the bound is attained. You can also bound the lambda invariant. This is less than or equal to lambda K over K plus 2 times SP over K. This is SP over the bit K minus 1. But now here it's something interesting. So this, when is this bound true? This is only true for all the K tilde in this neighborhood, epsilon Kn in a neighborhood of this K, epsilon script K of N. But there you need that the mu invariants to be equal. So you're going to an even smaller subset in the neighborhood, say satisfying that the mu invariants are the same. So you can't completely get rid of this mu invariants needing to be equal. Okay, so if the mu invariants are equal, then you can bound the lambda invariant. So that is somehow Kleine's result. And so we were motivated by these 2 questions as well as this MH of G conjecture. So let me say, yeah.
So this basically tells you that this Iwasawa modules are kind of sieve over this P projective space.
Yes.
Ah.
Yeah.
Then perhaps attained, right? Projective space is projective.
Yeah.
Just by algebra geometric argument.
Yeah. So, right. So now, yeah, let me spend a few minutes on this MH of G conjecture. So this MH of G conjecture, where does it hold? Of course, for a long time, once going back to the history, when the non-commutative main conjecture was formulated, if you look at the early papers of Coates and Hausen and Harris and so on, they had a, for a long time, it was a conjecture that the Selma group over the big extension is actually torsion as an Iwasawa module. And they had no examples, not any numerical, and John used to be very, very bothered by it, that here's a conjecture, because he always, that's one of the things I learned from working with John, that whatever statement you make, try to find one numerical example, because it might be an empty statement. There might not be anything which satisfies the hypothesis of that theorem. And so he was really bothered by it. And then Hashimori and Matsuno, they proved this very nice result, which more or less said, if you have mu equals 0 for a number field, let's work in this context, mu equals 0 over the cyclotomic extension, then all those elliptic curves gives, in fact, examples of being torsion over the trivializing extension. So then immediately you had a large class of examples. All elliptic curves with mu equals 0, they give you examples where they become torsion, where the Selma group becomes cotorsion over the trivializing extension. Okay, so that is the only class of examples where you know that the MH of G conjecture holds. So let me write that. So if mu equals 0, mu cyclotomic. I'll write mu cyclotomic equals 0 for x of E over K cyclotomic. Again, this is more general, not necessarily in the ZP2 case, more generally true for even in the non-commutative extensions or what is called the p-adic admissibly extension case. So then you look at x of E over K infinity. This is lambda G torsion. Again, here G is ZP2, but I want to remind you that for this statement, this is true for the P admissible G. Okay. And moreover, and mu, when I go, there is a mu invariant defined even for this object. Mu of x of E over K infinity is in fact equal to this, and then it remains 0. So, and in fact, this is more general. When mu is 0, then you go up a P extension, and this was already known to Iwasawa in the class numbers when you were studying the class numbers. If mu is 0, then you go to a P extension and take the mu invariant of the corresponding cyclotomic extension, that still remains 0 in the ZP case, right? So here the mu invariant, if it is 0 here, nothing happens to it even when you go to the K infinity extension. And this was again a question which again I would be happy to hear from the experts or people who know more about this. I've spoken to Hida about this, and there seems to be some divergence of opinion. You can ask, so let's look at E over K. Let's take the CM case. So CM by imaginary quadratic extension, and then OK is the ring of integers of endomorphisms of E. And then you go to F where you attach the P division points, K of EP, and then you have F infinity, which is F of EP infinity. So then Galois group of F infinity over F. This is isomorphic to ZP2 extension. And Lila Schneps proved it in some cases under hypothesis on the class number of K. And Gillard has, and his students have many papers, and the result is that mu of this dual Selma group over this extension equals, I'll put this within inverted commas because there seems to be no final word on this. There's a lot of literature in the paper, but some people believe Gillard's result, some people feel that it's not complete, there is some gap, etc., etc. And I haven't understood where things stand. Okay, so but let's believe this. Let's believe that mu of x of E over K infinity is 0. So then in this case, okay, sorry, not K infinity, but let me write F infinity. So then the MH of G conjecture, the original MH of G conjecture with H cyclotomic will then tell us that mu invariant should also, if you believe under MH cyclotomic of G. If you believe this conjecture, then this will also tell you that the mu invariant of the dual Selma group over the cyclotomic extension, cyclotomic ZP extension also has to be 0. So on the one hand, when the mu invariant is 0, you get a class of examples where mu is also 0 at the top and it is lambda G torsion. And in the commutative case, when everything is commutative, then it is saying that I have mu invariant equals 0 at the top. And then if I specialize to the cyclotomic extension, then the mu invariant is 0 even there. Now, again, I don't know, but when we were trying to find numerical examples for our present work, I realized that it's still not so much in the literature, but what I heard from John was that all numerical examples known substantiate this. So in the CM case, you do have, when the mu invariant at the top is 0, then when you compute the mu invariant over the cyclotomic level, it is 0. But we tried actually laying our hands on concrete examples because that would give examples for some of the hypotheses that we had in our present work. And I didn't know where to look, and I couldn't ask John. He said it's there in the literature. I did ask him, he said it's there in the literature. And he attributed it to Greenberg, and he said it's a folklore conjecture. But then either people forgot about that conjecture or it was not folklore. Okay, so this would under this MH cyclotomic, this would say mu of x of E over F cyclotomic, F cyclotomic is 0. So we try to turn things on its head. On the other hand, when you study the mu invariant over the anti-cyclotomic extension in our case there, so then you ask, when can you say that, suppose I know the mu invariant is 0, let's say for the anti-cyclotomic extension. What can I say about a neighborhood? Or can I go to the cyclotomic extension using these techniques? Because you believe that the mu invariant should be 0. Can we give a theoretical result saying that is indeed the case by using this topology and studying the variation of invariance in this case? So that was what we set out to be. So I'll just state the result that we can prove. Okay, here is the first. Okay, this is maybe, I'll just say note. So I introduced this special class of H, this subset of all ZP extensions, which I called script H here. So the first thing to note, and this is easy, when I take the cyclotomic ZP extension, this is in fact in this class. Okay, so therefore I have something to stand on. And then here is the analogous proposition. So let me call it 2. I call this lemma 1. Let me stick to that numbering so that I don't mess up.
For this definition, K is abelian over Q or any field.
For this one, let me still work with K abelian over Q.
Oh, okay.
Okay. Ultimately, our results are only in that situation. Though again, there I feel if we work hard enough, we can take a broader class of K, but okay. So the first proposition is this: for all but finitely many, intermediary extensions in this H, not E, but in this subset H. You indeed have MH of G conjecture. So we have Y of E over K infinity fixed by this H is a finitely generated, sorry, not fixed by H, Y of E over K infinity is a finitely generated lambda H module. Okay, right? So you have this extension here, K infinity. Then I have this K cyclotomic here. I have K. Now I'm taking some other extension, which is fixed by H, and this is a ZP extension here. And then I'm looking at the Selma group here, killing the P primary torsion part. And then the MH of G conjecture originally said that it should be finitely generated as a lambda H cyclotomic module. But what we can show is that for this subset, you in fact have the analog of the MH of G conjecture. Okay, so this somehow is guided by what happens for the lambda invariant. In a neighborhood, you know the behavior of the lambda invariant. Yeah, oh, sorry, the mu invariant. Exactly. Throughout, I'm assuming, yeah, okay. Throughout, I'm assuming that this is the case. In fact, it's, I started with already my E, remember, yes, okay, this subset, you need that it is torsion. Okay, but in some cases, we can even show that, you know, once it is finitely generated as a lambda H module, it has no choice but to be torsion. Right? It's finitely generated over a subalgebra whose Krull dimension is strictly smaller than the Krull dimension of the original module, original algebra. So it has to be torsion. Right? Okay, but this was again John's belief that it is torsion there because there is a phenomenon like this happening. Because what are you killing? You're killing the P torsion, which is anyway torsion. And then what remains has to be torsion, and in fact, torsion for a stronger reason. Torsion because it's finitely generated as a lambda H module. Okay.
So your John is John Coates.
John Coates, yes. No. Exactly. Yes, we don't know it. And our hope was, okay, the way we approached this was, okay, we are guided by all this, that the lambda H torsion should behave like the lambda invariant. You have these results for the mu invariant and so on. So find some place where that is lambda, where the analog of MH of G conjecture holds, and then see if you can move along to cyclotomic extension through a neighborhood, or that we still haven't managed to do. Okay, all right, so now, so here again, so the idea of proof, it's every proof in all of this, even though when you look at it, it's believable, and especially when you assume that it is torsion, then that's a very strong hypothesis, then you feel all this should be easy, but most parts, when you get down to the nitty-gritty, it gets technical. And so for instance, in this proof, you had to, the ingredients we use, you had to go back and analyze and sort of understand Monsky's M0 and L0 invariants and what they had done for the class groups. And then try to see how much of that can be pulled to the Selma group of elliptic curves. Okay, so those are the ingredients in this proof. And now I don't have much time. So let me just say ingredients of proof. So you use Kutzko, Monsky, what they do for the class group, and try to imitate, follow your nose, as somebody said, and see how much of it can be transferred to Selma groups. And along the way, we noticed that we had to keep adding hypotheses. So for instance, when we initially went with this subset H, we tried to, for instance, we didn't have this. We tried to see how much of this works without this hypothesis. Then we immediately had to make this hypothesis. Or we said, okay, let's avoid splits completely and then see what we can do. Then you had to come back to the splits completely. So those kind of hypotheses, we had to keep adjusting. All right, so now let me state this theorem. And then I'll give one numerical example. Well, I'll say some applications. So for any HAB, remember this way of parameterizing, sigma A tau B in H, the topological closure of this, the following are equivalent. First, that y of E over K infinity is finitely generated over lambda H prime, where H prime, I'm just going to shorten notation. This is K infinity fixed by HAB. So fixed by this one-dimensional subgroup, that's what I'm calling H prime. Instead of writing K infinity HAB, I'm just going to call this H prime. So if that is finitely generated, and then this translates to a very systematic behavior of the mu invariants. P to the power n times mu G, the mu invariant of the Selma group, x of E over K infinity. This is in fact equal to mu Gn mod Hn prime. So this is Gn mod Hn or the corresponding gamma Pn's, right? Just forget the n's for a minute. G is a Zp2. H prime is a Zp. So G mod H will be a gamma. And this Gn mod Hns are really like the gamma Pn's of that gamma. Okay. So this x of E over K infinity fixed by Hn prime for all n. So Hn prime is again the P to the power n quotient subgroup of Hn. Sorry, of H prime, right? H prime is isomorphic to Zp. So H prime mod Hn prime is isomorphic to Z mod P to the n. So it's the usual P to the power n index subgroups that you have in a Zp extension. So this is a very systematic growth. So in particular, when the mu invariant is 0, then it continues to be 0 all the way. So the MH of G conjecture, and this we already knew from trying to understand the cyclotomic extension, we knew that the growth of the mu invariant is somehow crucially linked to the MH of G property. There is a systematic way in which the mu invariant is growing, and ultimately it forces the mu invariant at the top and below to follow some rules. And that's when MH of G conjecture holds true. Okay, so that's the second. And then I'll write, there are other statements, but I'll skip them for want of time. So now I look at the lambda invariance of the dual Selma group. This is bounded. So now by this lambda invariant, I mean, so each of this L in a neighborhood, once I write this, it will be clear, in a neighborhood of K infinity H prime. So now this K infinity H prime over K is a gamma extension. So you can talk about a neighborhood of K infinity H prime. And then you can, so these elements L are in a neighborhood of this K infinity H primes. So each of this script L is a ZP extension of K. And then the lambda invariant is bounded in that neighborhood. And then you can go back and translate this again, which I'm not going to write. You can translate this to the lambda, the corresponding H ranks, because you have rephrased it in terms of this lambda H ranks. So you can go from this lambda invariant to that and back and forth. And in fact, that's how we prove it. And the ingredients are again, because again here you need the hypothesis that it is torsion. So you have something that's torsion over a ZP extension of K, and then you're climbing to another ZP extension, and you do a control theorem from that ZP layer to the top ZP layer. So you're doing a control over that ZP for these H's. So those are the ingredients. It's highly technical, and the proof, some parts of it are easy, but to make this precise, so for instance, typically this part might be easy to see. But to show that the converse is true, you'll have to come here and then understand what is happening to the mu invariants in the neighborhood and then go back or things like that. So they're sort of really intertwined. So we cannot, in fact, at one point we said, okay, this last statement is too ugly and it's not really shedding light on anything. So let's drop that and try to prove the statement without that. But then we discovered that it was getting uglier or we couldn't prove it. So we put back the technical statements. Okay, so I'll stop here as far as the main theorems are concerned and just state a few applications. Which again are interesting in their own right. The applications. So the first is first striking application. We were quite struck by this application. There's an old conjecture of Mazur. So conjecture of Mazur, not the usual cyclotomic Selma group being torsion, not that conjecture, but this conjecture, I myself wasn't aware of this till we started working on this paper. Yeah. Oh, okay. Okay, conjecture of Mazur, which states the following. So the model way rank, thank you. So the model way rank of elliptic curve, as the elliptic curve that we have fixed and the P that we have fixed of E stays bounded along ZP extensions of K unless the extension is anti-cyclotomic and the root number of the elliptic curve is negative. So this is a conjecture of Mazur that I was not aware of. And our way of coming down from the top to understand what happens at the intermediary ZP layers, in fact, gives us sufficient conditions. So that was the first application. I thought I erased something somewhere. Okay, let me continue here. Sorry? Negative, yeah, -2. Thanks, yeah. So one of the first applications is we derive sufficient conditions for Mazur's conjecture to be true. And let me give you a flavor of these sufficient conditions. So for example, P odd, it's unramified in this totally abelian extension, unramified in K over Q. Then the rank is 0 over K. The model way has rank 0 over K, and is finite. So the P primary part of the Tate-Shafrevich group, if it is finite and the rank is 0, then you know that Mazur's conjecture is true. So this is sufficient. And then we have some more conditions in terms of K and also its quadratic twist. When it is totally imaginary, then you can express a condition with rank 1. When rank is 1, then you have we understand sufficient conditions for that to hold. In terms of the rank of E over K and its quadratic twist. So let me not spend time writing it down. So that's one. So again, we had to spend a lot of time to actually find examples, concrete examples of elliptic curves where we can apply our theorem. And we have quite a few, but let me write down one. This is 43A1 in Cremona tables. The quadratic extension, we could only still do this only for small primes. Already doing it for 5 or 7, we had to, it was enormous computation. And P are these primes, 11, 13, 17, 19. So there's a trade-off. When you work with small degree extensions, you can maybe go to larger primes, but even that's hard. And then if you enlarge your K, then you can barely do anything even for the small primes. Okay, then the other application, which is again very interesting, is there is this other conjecture of Greenberg, the famous isogeny mu equals 0 conjecture, right? Greenberg conjecture, let me just say it, I won't write it. So which says, Greenberg says, take an elliptic curve E over Q. And then if the Selma group over the cyclotomic extension over Q, cyclotomic is lambda gamma torsion, then there's always a Q isogenous elliptic curve whose Selma group has to have mu invariant 0. Okay, so this is when mu cyclotomic equals 0 and isogeny. I'll just say so that you know which Greenberg's conjecture I'm referencing. So we can also, surprisingly, this approach also gives us a large class of cases which seems to be new. So we can establish this conjecture. For a maybe new, we still have to check. Okay, and so then some more applications, because this was what was, if you look at the history and look at all the results there, one of the reasons that they did all this was because they also wanted to understand Iwasawa's formula, right, in terms of lambda, mu, and E, the growth of the class number, the P part of the class number in ZP extensions. They wanted to see if there are analogous formulas for other ZP extensions. And that's where the invariants L0 and M0 come in. They are the ones that hold the place of lambda and mu. And E, that's where Monsky has to do a lot of work. And sometimes he says, oh, I believe there's an E. Oh, no, but there cannot be an E like that, you know, and so on. So therefore, again, we have those applications, growth, both of model way ranks, growth asymptotics. along the finite layers, Fn, what did I call it? K infinity, right? Along K ends. So you have K infinity. And this typically will be a Z mod Pn cross Z mod Pn. So for such intermediary layers, you get some Groth asymptotic patterns for the model wave rank of the Selma group and so on. Okay, so that's the next application. And yeah, this is interesting again, but how much time do I have? I don't have time, but it also tells us with these methods and with some more hypotheses, which are a little technical and which depend on the, your elliptic curve has good reduction, right, at the prime P. So therefore take an error model and look at the special fiber. And then look at the Kodaira type. You have the classification of elliptic curves according to the special fiber, the Kodaira type. So if you make additional hypothesis on that Kodaira type, then we can actually get examples of what I alluded to here. That the mu invariant should be 0 over the cyclotomic extension. So like I said, John Coates had somehow led me to believe that in all numerical examples, where you know that the mu is 0 at the top in a CM extension, ZP2 extension, when you specialize it to the cyclotomic extension, it is 0. But then I couldn't find any such examples. And of course, then I realized that there isn't even unanimous agreement about whether mu is 0 at the top, given that Gillard is sort of, there's mixed feelings about Gillard, to put it mildly. So therefore, you don't even know if mu equals 0 at the top. But you know mu equals 0 for many examples, but that's going through the cyclotomic case. You know that the cyclotomic, okay. So in the CM elliptic curve case, so if you're assuming everything is CM, let's say K equals F. So then you have K cyclotomic, this is a ZP extension. Then you have the K anti-cyclotomic. And this is the trivializing extension. And then you also have these two other special ZP extensions. Now, because it has good ordinary reduction, my P here breaks up into pi pi star. So you have the K E pi, and then you have the K E pi star. So you know that the mu invariant is 0 here. This is Sinert, Leila Schnips, there's no problem with this. And I think Perariu also gives another proof of this. And then you know that the mu is 0 for these two ZP extensions. So therefore, once you know that mu is 0 at any intermediary ZP extension, then it has to be 0 here. So if you grant that mu equals 0, then you're asking what happens if I come down to the cyclotomic extension? Is it 0? And so we can give examples or conditions under which that happens. So we give sufficient conditions for this to happen. Unfortunately, it's very technical, the kind of hypothesis we need to add. But again, thankfully, we are almost in the process of completing our work to find a numerical example where all the hypothesis holds, and you can find the mu equals 0. So I'll stop here and thank you very much.
So are there any questions or comments?
So you've been showing that the lambda and mu invariants are bounded in certain neighborhoods. Do you expect that these invariants are actually locally constant, perhaps off a finite number of points?
Well, mu you saw was, I don't know, lower semi-continuous, but if it is 0, then it remains bounded, then it remains 0 in a neighborhood.
Mm-hmm.
Lambda is more tricky, and I still haven't understood the full story of Monsky's proofs. There are some very nice results where you can show that it's O of 1. It's all bounded by a constant. Mm-hmm. There's an absolute constant in a neighborhood. But then surprisingly, if you go look at some other paper of Monsky, he will say, I don't see a reason why this should be true. So, and he has written some 10 papers on this subject, and it's a bit too much for me to look at the chronology and say which paper should I take for granted.
Huh. So you don't really know.
No. I think it merits a workshop of this order to understand all of Monsky and Kutzko-Monsky.
Any other questions?
I think again, this was bounded. I mean, this was inspired by the expectation of what happens to lambda in a neighborhood, right? There was that result. That was Greenberg's conjecture also, and which was already proved by Greenberg for some cases. That in a neighborhood that you expect it to be bounded, but maybe Hida can say more. And I think Mazur was inspired by that. Because the lambda invariant is the closest you have to understanding. If you believe that the Selma group is torsion, right, then the lambda invariant somehow can control the model Weyl rank. Once you grant that
But
Shah is finite.
P is the prime of ordinary reduction still, right? In that conjecture.
Sorry?
P is ordinary in that conjecture.
Exactly.
And yet the model Weyl rank is not bounded in that particular anti-cyclotomic extension.
If
Okay.
it is, well,
yeah.
maybe the answer is I
That's very
still
interesting.
fully you don't know. But this was Mazur's conjecture, again, which I was not aware of till I started working on this problem.
Where is it made? Is it in
I can
print
give
or-
you the reference. I don't remember it offhand, but
Any other question? Okay, so let's thank speaker again.